Hello, so today we're going to talk about L'Hopital's rule for evaluating limits. Now, quick warning, if you have not understood derivatives, there is no point watching this video from this point on. So what we're going to do is L'Hopital's rule applies the knowledge of derivatives to evaluate limits that are in their indeterminate form. Without derivatives, you can't do this, and if you don't understand derivatives, you can't continue on with this video. So, if you don't understand the derivatives, please stop watching and move on to the different derivative videos that I've made or that other people have made. Now, indeterminate forms are when you have stuff like 0 over 0 or infinity over infinity. Those are considered indeterminate forms of a function. For example, if I plug in negative 1, we get 2 times negative 1 squared, negative 1 plus 1. This becomes 2 minus 2. We get 0 over 0. And if I want to find the limit of this, well, I would just simply factor it. This is one of our rationalization techniques. We talked about that last time. So we would factor this out. I'd get 2 times x squared minus 1. We'd factor the x squared minus 1. And I'd cancel stuff out. Here, again, same thing. If I were to just work out this problem right now, by plugging in infinity, you get infinity over infinity. So we had talked about last time by dividing the highest power by both top and bottom by the highest power of x, which in this case was x squared, we can adjust the problem so we can evaluate this. We get 3 minus 1 over x squared, 2 plus 1 over x squared, and again, anywhere the variable was in the denominator, it now became 0. We go to answer 3/2. This other answer right here would have been a negative 4. And that's all fine for the last couple of times. Manipulating algebraically isn't that bad. But there are some problems where you cannot manipulate algebraically. If I were to plug in 0 into this problem right here, we get either 0 minus 1 over 0, which is 1 minus 1, which is 0. And if you remember from last time, we had the limits as x approaches infinity. I believe it was sine of 2x over x, which was infinity in the bottom, and then this right here, sine of infinity, is unknown. Can't really work that out. There are ways to manipulate both these problems. Well, yes and no, there are ways. But for the most part, they're not really efficient ways to work this out. So we don't want to really deal with that. So there is another way where, as you've already learned, limits allow us to find derivatives. They're actually the formal definition of the derivative. I can then work backwards. I can use the derivative to evaluate a limit. And that's L'Hopital's rule. This tells us the limit as x approaches c of f of x over g of x is equivalent to the limit as x approaches c of the derivative of f divided by the derivative of g. That's how L'Hopital's rule works. You take the derivative of the top and the derivative of the bottom, and then evaluate. Now, this rule only works under the following conditions. The form of the original limit must be indeterminate, and then obviously both derivatives must exist. If it's not indeterminate form, you don't need L'Hopital's rule. You still just plug in normally. And that's how you always evaluate limits. You always want to plug in first, unless the directions tell you apply L'Hopital's rule to solve this, in which case then you go ahead and apply it. But if it just simply says evaluate the limit, like all the problems will say on the AP test, you want to actually plug in first and see what happens. If it's indeterminate, L'Hopital's rule will be the quickest way to go about solving the problem, for the most part. It's just simple derivatives and then plugging in again. And the nice thing about L'Hopital's rule is after you do your derivative, if it still is indeterminate, you can do a second derivative, and then a third derivative, and so on, until you get down to the point where it no longer is indeterminate. It will eventually work out, whether as an actual number or as a does not exist function. So for example, if I were to plug in 0 initially, as we saw before, we got e to the 0, which was 0, we got 0 over 0 for this problem. So I'm going to apply L'Hopital's rule and take the derivative of the top. Derivative of e to the 2x is 2 times e to the 2x. Derivative of 1 is 0. Derivative of x is 1. Just left with 2 times e to the 2x. And now when I plug in 0 for x, I can now actually evaluate. The limit is 2. Now, we could have found that if you actually graph this function and see what happened as x is approaching 0. That is perfectly fine and perfectly legit. That is no big deal there. Or if you use a numerical way of plugging in numbers that are close to 0, like 0.1 and then 0.01 and then 0.001, and same thing from the negative side, you would eventually see it's getting closer and closer to 2, but not really the best of options. L'Hopital's rule, very quick, very simple. In this case, we have the limit as x approaches infinity of natural log of x over x. Well, natural log of infinity is infinity. X is still also infinity. It's an indeterminate form. So instead, I will apply my derivative. Derivative of 1 of a natural log of x is 1 over x. Derivative of x is just simply 1. I now plug in infinity for x. 1 over infinity is 0. And again, if you were to graph this, you'd see that. The key is, as I've said numerous times, not all problems on the AP test, or not all problems on your test in your class, will allow you to use a calculator. Hence why this is a very important and very useful rule. So I want you to go ahead and apply L'Hopital's rule for this particular problem. As x approaches negative infinity, plug it in and see what happens. As you can see, you're going to get infinity over infinity, so when we take our derivatives, notice we still get infinity over infinity. Don't want that. So what we have to do is we have to plug it in a second time. Do a second L'Hopital's rule. And you get 2 over e to the negative x. Now when I plug in negative infinity into this problem, we get, again, infinity for the denominator. But because the numerator actually has an actual number, it is no longer indeterminate. And that's what's okay. That means this right here is really just 0. Okay? And in this case right here, this is not necessarily an indeterminate form, but you should remember, e to the negative x, I can rewrite that. Not necessarily a rational function. This is equivalent to the square root of x over e to the x. Now it's a rational function, and again, when I plug in infinity, I get infinity over infinity. So I'm going to take my derivative, which is 1/2 x to the negative 1/2 over e to the x. So I should really rewrite this as 1 over 2 square root of x e to the x. At this point, I now have a number over a function that is no longer going to be indeterminate. When I plug in infinity, I still get an infinity in the denominator. And my answer is still 0. That's how L'Hopital's rule works. If it's already an indeterminate form, 0 over 0, or infinity over infinity, you can take the derivative of the top and the bottom of your fraction and then evaluate further from there after you simplify it. If it's still indeterminate, as we saw in this example, you take a second derivative, and if it's still 1, you take a third, and so on. Once you get to the point where you pretty much have a number over your expression, or your expression over a number, then you're going to have a problem where it's no longer indeterminate. You can actually get an answer. 0, infinity, actual numbers, whatever it works out to be. So that's how L'Hopital's rule works. That's our end of our discussion on limits. Again, at this point, you've already finished discussion on derivatives anyway, but this is the last thing we need to talk about with our limits. So I will see you next time.